Hi there. Welcome to the content highlights for Chapter 11.1, 11.4, and 11.6. In these sections, we will investigate probability and counting techniques. A New York State license plate is a combination of 3 letters followed by 4 digits. How many different license plates can be manufactured for New York State? To do something like this, I would recommend you start by drawing out what this would look like. Give yourself an open sketch. So we said that the first 3 pieces of that license plate are letters, followed by 4 digits. They've told us there's no restrictions on what we can use, which means that we have 26 letters that could be for the first letter, 26 for the second, 26 for the third. Again, no restrictions here. And then we have to follow that with 4 digits. Well, digits are 0 through 9. That means there's 10 of them. So we have 10 possibilities for each place. Now, using the multiplication rule, we're going to go ahead and multiply all of these together, giving us 175,760,000 different possible combinations. Now, what if instead we go from having no restrictions to restricting that we can only use odd digits on the license plate? Just like we did before, we can still have our 3 letters, but the number of digits will be different. So no restrictions on letters, so it's still 26 times 26 times 26. But what are our odd digits? We have 1, 3, 5, 7, and 9. That means we have 5. So these are going to be 5 possibilities each instead. Same thing, using our multiplication rule, we get 1,098,500 possibilities. So we can see what a difference it makes by just cutting the number of digits you can use in half. There's obviously a fraction of the amount of possibilities in that aspect. Next, let's consider the sample space for having a family of 3 children. So we're referring to the gender of each of those children. Now, we've already given the sample space here, so there are 8 different possibilities of what could happen because you're considering the gender of each different child. So your first child, second child, third child. Find the probability of having more than one, so this is really important here, male child. So more than one male child, we could write it like this. So probability of more than one means greater than one male. And then we need to go into our sample space and just count which of these have more than one. Well, if you have 3 kids, more than one could be either 2 male children or 3 male children. So which of these situations have more than that? So we have 3 male children, that counts. 2 males, 2 males, 1 male, nope, 2 males again, and all the rest have either 0 or 1. So if we count those up, we have 4 out of 8, which reduces to 1/2. So that means that in a family of 3 children, 1/2 of them, 1/2 of the time, so the probability of having more than one male child would be 1/2 or 0.5. Find the probability of having 5 female children. So we're looking at the probability of 5 females. Well, think about this for a moment. If you have a family with only 3 children, could you have any more than that? Absolutely not. This is what we refer to as an impossible probability because it's something that could never actually happen. It's very similar to the concept of if you're dealing with a standard deck of cards in which the colors are only red or black, and I said to you, what is the probability of selecting a yellow card? Well, there's only red cards and black cards, so there would be no yellow cards. So impossible probability, meaning it can never possibly happen. Next, let's take a look at dealing with tables, so tables of values. The table shows the educational attainment of the population of a small city ages 25 and over expressed in thousands. What is the probability that a randomly selected person from this city is female or has completed 4 or more years of college? So writing this out, we are looking for females or more than 4 or more rather years of college? Well, let's see, we have a total of 85 females. We have a total of 47 who have completed 4 or more years of college. Of course, these are in thousands. However, we also have this overlap. So that means that 23 was counted in this total and this total. So we have to use our exclusion rules and we can add those together. So we have 85 out of the total plus 47 out of the total. But then we're required to subtract out the overlap, which is 23 over the total. This gives us 109 out of 171, so that would be the probability that this situation will occur. You can, of course, reduce this if it reduces. In this case, it is reduced all the way. Last for this section, let's take a look at Venn diagrams and see how those relate back to probability as well. How many students speak Spanish or Chinese at home? Well, Spanish or Chinese means that we're looking for every single student in the Spanish circle and every single student in the Chinese circle. So we need to add those up. So we have 7 plus 3 plus 8 plus 33. Those are all in the Spanish circle. Plus, we already counted the 3 and the 8, so we still need to add 13 and 2, which gives us 66. Another way to complete this problem would be to do the same thing we did in the previous example when dealing with females in education. You could add them both up and then subtract the 3 and the 8, which is overlap. You will get the same answer either way. Now, I know it doesn't ask it on here, but how is this similar to a probability? Well, if we wanted to know the probability of this event occurring, you would take that number and then divide by the total number of people who are surveyed. So it's as simple as that. Take what you're looking for and divide it by the total. How many students do not speak any of these languages at home? Well, because they've already given us on the outside, anything that's beyond the boundaries of the Venn diagram circles means that that is not included in those values. So there are only 4 students who do not speak any of those 3 languages at home. Thanks for watching.